We're going to take a look at some aspects of cellular metabolism, and this will take a few videos. We're going to break this down step by step, and one of the things I'm going to ask you to do first is kind of review and think about what you already know about ATP, because a large part of what we discuss here is going to be answering the question, how do cells make ATP, or where do they get their ATP from? That's part of why we're having this discussion. I'm also going to ask you to review what you know about enzymes, because those are going to be critical factors in doing these metabolic processes. And I'm going to talk about, to start this off, coenzymes. This is not a term that we've really gotten into very much. Obviously, they have something to do with enzymes, otherwise they wouldn't have enzyme in the name, but coenzymes are not enzymes. We're going to need to discuss what they are. But before we get into that, one other thing I want you to review. Please go back and look at the oxidations and reduction video. We've talked about redox reactions or reductions and oxidations and specifically what they are. And also review the web link entitled How NAD Works. NAD is the name of a coenzyme. It's one we're about to talk about. And if you see this video ahead of time, it'll give you a little bit of background before we dive into it in a bit more detail. So again, this is one of my videos and this is one of the web links. Please pause this video or stop this video. Go back and make sure that you're well situated there and then come back and continue on. So our discussion about coenzymes, there's one other thing I have to remind you of that you already know before we go on any further with this. And it has to do with hydrogen. You know what a hydrogen atom looks like. We've been talking about hydrogen atoms since the first day of class. So just by means of review, let me remind you that a hydrogen atom consists of one proton in its nucleus. There is one proton. And one electron. Right? We'll make that dot be an electron. So there's a hydrogen atom. I just want to remind everybody of that. I'm going to use this as a shorthand way of representing hydrogen atoms in this particular series of videos. The plus sign is a proton, the negative sign is an electron, so that's going to be my way of representing a hydrogen atom in the next couple of videos, okay? Just so you're clear on that. Okay, so with that in mind, let's talk a little bit about coenzymes. First of all, what are they not? Coenzymes are not the same thing as cofactors. We've discussed cofactors before, and we said that cofactors are small, or well, they're metal ions that are going to assist an enzyme in doing its job in some way. We've talked about that back when we did enzymes recently. Coenzymes are not the same thing as cofactors. One difference is that coenzymes are organic molecules as opposed to metal ions. So right off the bat, they're very different chemically. Coenzymes, again, are organic molecules of some type, and there are lots and lots and lots of them. We're going to focus in on two of them in the very near future here. Let's say for the moment that coenzymes are organic molecules that assist an enzyme, as the name implies. Co, as in they're cooperating or helping an enzyme. They assist an enzyme in doing its job, but very differently than a cofactor does. We're going to look at two specific coenzymes in this upcoming discussion. Again, there are many of them. The ones we're going to look at are abbreviated NAD and FAD. NAD, I'll give you the full name of it if anybody's interested. It's nicotinamide adenine dinucleotide. I will spell that out if you're dying to know what it stands for. Nicotinamide adenine dinucleotide. But for obvious reasons, people just refer to it as NAD because it's just a lot easier. FAD is flavine adenine dinucleotide. But from here on out in these videos, I'm just going to say NAD or FAD. So there we go. These are similar molecules, but not identical. The role is actually pretty similar to a cell. Let's look at NAD first. So if you look on the first page of the cellular metabolism section of the lecture outline book, you'll see there's a reference to NAD there. We're covering this now so that we can get into that discussion with this basis, with this background. So let's talk a little bit about NAD. NAD is a coenzyme whose job is to assist enzymes that remove hydrogen atoms from molecules. Let me show you what I mean by that. There's a molecule called lactic acid. Small organic molecule, very common in biology. There's lots and lots of hydrogen atoms there. Right? I highlighted them in red. One of the hydrogen atoms, I'll do that. You can, I could do that for all of them, I suppose. But I'll put my little symbol here, my hydrogen atom symbol, over the one of them, and say, okay, that molecule has a lot of hydrogens. Think back to what you know about reductions and oxidations. I could say that that molecule is rather highly reduced. It's got a lot of reducing power. By saying that, I'm just saying it's got a lot of hydrogens attached. Remember, again, from that redox video that we had earlier, when I talk about a hydrogen atom, I'm talking about an electron equivalent. I'm saying, hey, there's a hydrogen atom. It includes an electron, and electrons are valuable. So if I have a bunch of these, I'm valuable. I'm highly reduced. I'm energy rich. I have a lot of potential energy, however you want to say that. So this molecule right here, lactic acid, is a rather highly reduced molecule. It's got 1, 2, 3, 4, 5, 6 hydrogen atoms, that each of which has value. So there are times in a cell when you might want to take lactic acid, rip one of the hydrogens off of it, and do something useful with it. It would be like saying I've got my wallet and I have 6 $20 bills in it, and sometimes I want to take one of those $20 bills out and do something useful with it, like purchase something. The thing is, an enzyme is going to be needed to reach in here and grab that hydrogen and remove it. But enzymes do their job over and over and over again, remember. So if the active site of that enzyme grabs that hydrogen and removes it and gives it to somebody else, it's got to give it to somebody else because it can't go back and do this again and again and again to other lactic acid molecules if it can't dump off or get rid of that hydrogen. In other words, for the enzyme who is interested in stripping away one of these hydrogens, for it to be effective, it's got to have somebody there helping it. It's got to have somebody that it can say, here, I'm going to grab this hydrogen, I'm going to hand it to you. I'm going to pick this up. Whoops. I'm going to pick this up. I'm going to hand it to you, and then I'm going to go find another lactic acid and do the same thing over and over and over again. So for the enzyme to be able to do its job properly, it needs an assistant, if you will, that can temporarily hold on to the hydrogens. It's like, here, hold this for me while I go do this again and again and again. So a reaction that is common in cells might look something like this. If I were to strip away that hydrogen atom, I'm going to wind up with this molecule. Give me a second to draw it here. I won't redraw the hydrogens in red. Let's draw them as is. This is a molecule called pyruvic acid. Again, a common molecule in biology. Fit them both on the screen here. Common, important molecule in biochemistry. And you can see that it's very, very similar to lactic acid, except it's missing a hydrogen, specifically that hydrogen. So if an enzyme were to grab onto lactic acid and rip the hydrogen away, like this, what do you have left? Well, you have that. You have pyruvic acid. The electrons that were being shared between the oxygen and the hydrogen are now being shared between the carbon, so you get the double bond oxygen. But still, pyruvic acid is lactic acid minus a hydrogen. So where did that hydrogen go? Remember, the hydrogen is valuable. It's an electron equivalent. It's it's money to a cell. So you got to do something constructive with it. You're not just going to rip it off and throw it away. I'm not going to take a $20 bill out of my wallet and throw it away. So somebody's got to hold on to this. Well, what if I have this assistant that I was describing? I have a coenzyme. What if that coenzyme is a molecule called NAD? So here's a molecule of NAD. I'm not going to draw out its structure. It's got a fairly complicated structure. We'll just represent it like that. And what if when an enzyme reaches in here and grabs onto this hydrogen, it hands it to NAD, like that. So by the end of this reaction, if I take lactic acid and NAD and let this reaction proceed, I'm going to have pyruvic acid and NADH. In other words, all I did, I being the enzyme, was I picked up this hydrogen, ripped it off, and handed it to NAD. Well, what does that look like? Well, here's my starting materials, here's my ending materials. Here's the pyruvic acid, in other words, this thing minus the hydrogen. Where'd the hydrogen go? Right there. That's the hydrogen. If you want to use another one of these little symbols there, that's that hydrogen up there. Wow, these things are harder to handle than I thought. There we go. That's that hydrogen. Okay. If you prefer, you can write this reaction a little more concisely, in a little more clean fashion. I can say lactic acid can be converted to pyruvic acid as long as there's somebody to hand that hydrogen to. So an enzyme is going to strip a hydrogen away from here, which turns this into that. But where'd the hydrogen go? It was accepted by NAD, which then became what we call NADH. It's just NAD with a hydrogen attached. So what I wrote up above in kind of a more complicated way is really more commonly written like this. It's just a simpler way to write this up. Both of these things are happening. These are what are called coupled reactions. They're happening simultaneous. You can't do one without doing the other simultaneously. So here's my reactants. Here's my product, if you want to put it that way. So this is a great example of a redox reaction. Let's fill in the details. If these two molecules differ only by a single hydrogen atom, only by a single electron equivalent, remember I'm using hydrogen atom and electron equivalent as interchangeable terms. If they differ only by a single electron equivalent, well, what happened? As I go from left to right, this molecule gained an electron equivalent. That's a reduction. This must be more reduced than that. So if I want to really highlight this, I can say this is reduced. I'll put RED for reduced. If I really want to highlight that this is less electron rich than that, I can call it oxidized. I'll put OX for oxidized. If I look back at my structures of these organic molecules here, my lactic acid had a hydrogen atom that my pyruvic acid didn't have. There was one more electron equivalent here than there. Therefore, this is relatively more reduced compared with this, or this is relatively more oxidized compared with that. Again, reduced means more electron equivalent rich, and oxidized means more electron equivalent deficient. So I can say that the lactic acid is more reduced than the pyruvic acid. If I want to really highlight this, it's the equivalent of somebody walking up to me, taking a $20 bill out of my wallet, handing it to a third person, and then stepping away. So the $20 bill is the hydrogen atom. So somebody took $20 away from here, gave it to this other participant, and by the end of all of that, I'm left $20 deficient. I have $20 less than I used to have, and that other person is $20 richer. They have $20 that they didn't used to have. This is a redox reaction. There's the oxidation here, there's the reduction here. Reduction, oxidation, that's redox. But the point of discussing this right now is to show you the role of NAD. It turns out that stripping hydrogen atoms off of organic molecules is something that happens constantly in cells for very valuable reasons that we're about to get into. So if you're going to do that, if enzymes are going to rip hydrogens off of organic molecules, somebody has to be there to hold them so that something constructive can be done with them later on. The somebody that's holding those hydrogen atoms are coenzymes such as NAD. So this is, in fact, NAD is the most common of them that will serve that function. So that's why we're discussing this now, because we're about to start discussing carbohydrate metabolism, and we need NAD to be a participant in that. Let me mention FAD. I told you at the beginning of this video that there's another coenzyme that we have to discuss today called FAD. FAD works in a very, very similar way as NAD, except it can hold 2 hydrogens at a time instead of 1. So let's say some other reaction, I won't illustrate another reaction just for simplicity's sake here, but let's say some other reaction results in some carbohydrate having 2 of its hydrogens ripped off. Here's 2 hydrogen atoms that came from some other source. Who's going to take those? Well, FAD could. In other words, FAD could certainly handle taking 2 of these, and it would become FADH2. Now, the nice thing about these coenzymes is the following. If I give NAD a hydrogen and then would like it to return that hydrogen to me later on, it will. I'll say, hey, hold this hydrogen temporarily. Later on, I might need it, and I'll say, give me that hydrogen back. And it'll say, sure, I'll give it back to you. Likewise for FAD. If I say to this FAD, hey, here's 2 hydrogens. You're now called FADH2. And then later on, I say, oh, I need 2 hydrogen atoms to do something useful. I need it for some metabolic process. I'll say, give me those 2 hydrogens back. It'll say, sure, I'll give you those 2 hydrogens back. Here they are. It's perfectly willing, FAD is perfectly willing to hand me back those 2 hydrogens. NADH is perfectly willing to hand me back its hydrogen. This may all seem very abstract, and I understand that it is right now because we haven't really applied it to metabolism. I've given you the one example of a reaction here. But we're going to be applying this idea of coenzymes, and in particular the idea of what NAD and FAD are doing in cells, to actual cellular processes. But I wanted you to know about these 2 coenzymes, this one and this one, before we got into that, because otherwise it wouldn't make any sense once we got there. So that's why this video is to just get you familiar with NAD and FAD. If that's not clear, please watch this again. Please contact me with any questions. Please rewatch the other 2 videos that I recommended, and I think between them all, you're going to come away with the notion that NAD and FAD are simply places to dump hydrogen atoms temporarily until you get around to using them. And keep coming back to the notion that hydrogen atoms are electron equivalents and they are valuable. So that's the introduction to coenzymes in general, but these 2 coenzymes in particular. Just as a final note, lots of other coenzymes exist, and they may serve functions that have absolutely nothing to do with holding on to hydrogens. They may do very different things. We're just picking on these 2 particular coenzymes today because we're going to need them in the immediate future.